Okay, let's continue. Now, pure semiconductor, they do actually, when temperature increases, they allow electricity to flow, but there is a way to actually allow more current to flow through, which means to allow more free electrons or more holes inside the semiconductor, and that particular process is actually called the doping process. All right. I know when I mention the word doping, some of you will be thinking of drugs and all that, but no. Okay. In physics, doping actually means a process which adds a certain amount of impurities, all right, another element into the semiconductor, into the silicon. That impurities, we call it as dopant, to a pure semiconductor to increase the electricity conductivity. Now, over here, please do take note, the explanation of doping is actually to add a certain amount of impurities, all right, to increase the electricity conductivity. They did not mention to cause it to be more electronegativity or increase the number of free electrons or positive, but it's a more general term. Main reason is because it can be both ways. It can either increase more electrons or it can increase even more holes. All right, so we're going to start back with N type of semiconductor. N type of semiconductor is actually produced by abundance of electrons. And previously, I did mention actually one thing. This N actually represents negative. Okay, this N actually represents negative. I need to adjust my camera a bit. I'm using a different type of spec, so the angle of my screen and my view is slightly different already. So this N type of the word N actually comes from the word negative. So it actually produces abundance of electrons in the semiconductor. Main reason is because, like for example, in chemistry, right? In chemistry, when you have an atom, all right, when you have an atom in chemistry, why the effect so like that? Okay, still like that one. All right. In chemistry, when you have an atom and they actually have more electrons, all right, more number of electrons compared to the protons, we call that atom to be negative ion. And when they have more protons compared to electrons, we actually call it a positive ion. Okay, so in physics, when the electrons is more than protons, it's actually negatively charged. And when there's more number of protons compared to electrons, we call it positively charged. So the word N here actually represents negative. Negative means that there is more number of electrons compared to protons in the semiconductor. Hence, it is more negatively charged, and that's why they call it as an N type of semiconductor. They have more free electrons compared to holes over here. Okay, so a silicon atom has four valence or outer electrons, which each electron is covalently bonded with another four atoms. What happens if we add a dopant? All right, this dopant is actually a phosphorus atom. Phosphorus atom actually has five electron valence. So you see at outermost you have 1, 2, 3, 4, 5 electron valence at the outermost orbit. So when we take a phosphorus atom and we put it inside the semiconductor, the silicon, all right, silicon has 4 covalent bonds. So, but phosphorus has 5 electrons. So 4 of the electron valence will be covalently bonded with the other silicon atoms, but there is a fifth electrons that is not bonded by any covalent bond. So if this is the case, this free electrons is free to move inside the metal. And hence, when it's freely to move inside the metal, it will be, if there's one phosphorus, then there's going to be one free electrons. But if they increase the number of phosphorus inside, even though a very small quantity of impurities, as long as there's enough free electrons to move to create out the current, all right, then the conductivity of the semiconductor has already increased. So for an N type of semiconductor, for N type of semiconductor, free electrons is the majority charge carriers, while the holes are the minority charge carriers. All right. There are still holes. The holes will be created due to the thermal release, the electrons that is released out due to thermal energy. All right. But the majority charge carriers over here will be the free electrons. Okay, since the pentavalent atom donates an extra electron, hence it is also known as the donor atom. Examples of the dopant are the pentavalent. Penta means 5 electron valence atom. Right? Examples of these donor atoms is phosphorus, arsenic, and antimony. And since this is no longer in your basic, so just get it as an introduction for you guys, only a knowledge for you guys. P type of semiconductor, I think you guys can guess from now, the P actually stands for positive. All right, this positive actually means that they have more holes compared to electrons. So how did the holes come from? All right, the hole actually comes from a trivalent electrons. All right, it comes from a trivalent atom, whereby example aluminium. Aluminium has 3 electron valence on the outermost orbits only. So when it's actually being mixed into silicon pure semiconductor, silicon needs 4 covalent bond because it has 4 electron valence, but aluminium only has 3. So which means one of the electron doesn't have any pair for the covalent bond. When this doesn't have a pair, which means this is a hole, an empty seat. Okay, so what will happen is when the temperature increases, the electrons will start to move. It will actually jump and fill up the hole. Okay, so when it starts to fill up the hole will now become the majority charge carrier, while the electrons, while it's moving, it will become the minority charge carrier. All right, so the holes are the majority charge carrier, while the free electrons are the minority charge carrier. And since trivalent atom accepts electron, it is actually called the acceptor atom. An example of a trivalent atom is boron, aluminium, and gallium. Okay, so hence now you know P type actually stands for positive type semiconductor, majority is holes. N type is negative type of semiconductor, majority is free electrons. All right, so this is comparison between the N type and P type. Pure semiconductor, usually we use is silicon or germanium. The dopant material for N type is pentavalent because we want more electrons, so that's why we need 5 electron valence atoms. They are phosphorus, arsenic, and antimony. And then it will produce an abundance of free electrons in the semiconductor. Okay, and over here, majority of the charge carriers are free electrons, while the minority charge carriers are the holes. For P-type semiconductor, we want it to be positive. All right, when it's positive means there are less electrons. So trivalent atoms, they only have 3 electrons valence at the outermost orbit. Hence, it will create an abundance of holes. And majority charge carriers are holes, and the minority charge carriers will be the free electrons. All right, so that's the P-type and the N-type semiconductor, and hence now we are back into your syllabus, diodes. Wait, All right, so semiconductor diodes, diodes is actually the basic whereby they join a P-type and an N-type semiconductor together. Now, a diode is a device that allows current to flow in one direction but blocks the opposite direction, hence the LED. All right, the light emitting diodes. Now, one tips for you guys for diodes or transistor, the tips is the arrow always points to the n-type semiconductor. All right, the arrow always points towards the n-type of semiconductor. Why? Because it's always from positive to negative. It shows the direction of current flowing. Current flows from positive to negative. All right, so P is positive type of semiconductor, N is negative type of semiconductor. The arrow is actually pointing the direction of the current flow. It will always point towards the negative because current flows from positive to negative. All right, so this is one hint for you guys to see the direction of the arrow. Now, PN junction. So I'm going to use the simulation right now so that I can slightly take a rest. All right, so this is the PN junction. Okay, what happens here is if I were to, can I take this away? Tak boleh tutup ini hari ni. Okay. So over here, all right. So over here, what happens here is the power supply is actually not connected to the circuit right now. This is a basic circuit with a battery connected to a resistor or a rheostat, and then this is the PN junction. Now, which is which? Then you will have to see the dopant. This is boron, this is phosphorus. So my one particular way that I just recalled is the P, all right, stands for pentavalent. So phosphorus is a pentavalent atom. So pentavalent means they will allow more electrons. So hence, this right hand side, this blue color side is negative, N type of semiconductor. The boron part is actually the P type semiconductor. So when I forward bias, now forward bias is where the positive of the power supply or the battery is connected to the P type. Positive to positive, negative to negative, that's forward bias. Now when it's forward bias, electrons will flow. Right? When it's forward bias, electrons will from the negative to the N type, and then from the electrons will actually go towards the positive terminal. Okay, so this is forward bias. Now what you can see is that at this part, there is no breach. The electrons actually manage to come here. Okay, electrons is actually flowing from the negative terminal of the battery towards the N-type semiconductor, and it will come over to this junction. This middle part here is what known as the PN junction. And then the P-type semiconductor has a lot of holes. All right, so when the electrons move towards the positive terminal, the holes will move towards the negative terminal. It'll move towards this junction here. So the holes move to the junction, the electrons fill up the hole. All right. Why there's no hole over at this side? Because here N-type has a lot of negative free electrons. So we don't see that much of holes on the N-type. But at the P-type, the holes keeps on appearing because there's insufficient electrons over here. But this is a forward bias. Let's see what happens to reverse bias. When you see a reverse bias, notice that the electrons doesn't move. All right, the electrons obviously doesn't move because here is actually negative, but this is P type of semiconductor. All right, so when the P type semiconductor is connected to the negative terminal, the electrons cannot move through the junction. Okay, and then here all these electrons are already attracted to the positive terminal. So electrons main thing is that you need electron to flow at the PN junction. Let's go back here. So when there are, you see, when the electrons can come the towards this junction and the holes move towards this junction, electrons can pass through. All right, and that's how the whole entire circuit actually allows to flow. But if all this, you notice that the electrons is moving towards the right and then it stopped. The holes move towards the left and then it stopped also. Why? Because all the electrons from the N type of semiconductor has already been attracted by the positive terminal. And then all the holes of the negative terminal, the electrons are all over here. They don't even want to go any further. All right, so there is a very big, the PN junction is not functioning that well for a reverse bias. Okay, so that's a simulation for reverse bias. Now let's go back to the PN junction. Okay, a PN junction is formed when an N-type and a P-type semiconductor are joined together. The boundary between the N and P-type is called a junction. Okay, so holes from the P side similarly will move to the N side where they combine with the electrons. So the most important thing is that you want the electrons to N-type go towards the holes at the P-type, and the holes need to move towards closer towards the N-type so the electrons can actually move. Okay, so when the electrons and the holes can actually meet at the junction, it is actually considered as a forward bias. All right, so if they don't, all right, the region where the junction is left with neither holes nor free electrons, it is actually called a neutral region of a depletion layer. There is no charge carrier and it will become a poor conductor of electricity. All right, when we talk about forward bias and reverse bias, it will be much more easier for you all to understand. All right, so let's talk about forward bias. Okay, I'm going to start drawing myself ready. Now, forward bias, giving you guys a main overall view right now first. Forward bias, the arrow will always point towards negative. So this is N type, this is P type. All right, and this is a diode. Okay, I'm just going to build a simple circuit, power supply. Okay, so if the positive terminal of the battery is connected to the P-type semiconductor, the negative terminal of the battery connected to the N-type semiconductor, current flow for the battery is from positive, and if the direction of the current flow is the same as the direction of the arrow of the diode, then this is considered as a forward bias diode. All right, this is a forward bias diode. But if positive left, negative right, this is the N type, arrow always point towards the N type. Okay, my diode is like this. But if you notice one thing, the positive terminal of the battery is connected to the negative terminal. So when current flows, it moves supposed to move from positive to negative, but look at the direction of the current. Our power supply current is pointing towards the left, but our diode is pointing towards our current is pointing towards the right, but our diode is pointing towards the left. They're against each other. When they're against each other, this is actually known as reverse bias. All right, this is known as a reverse bias. So another hint for you guys to see is actually the positive terminal of the battery is connected to the negative terminal of the battery, which is wrong. All right, it's supposed to be positive terminal to P-type semiconductor, negative terminal of the battery connected to N-type semiconductor, baru forward bias. Okay, so now let's talk about the depletion layer. Okay, if it is a forward bias, positive connected to P-type, negative terminal connected to the N-type. So what happens here is P-type has a lot of holes. So I'm just going to draw 4 holes. N-type has a lot of electrons. Okay, so when the circuit is complete, power supply runs, electrons from the negative terminal will move towards the N-type. All right, when it moves towards the N-type, it will repel all these electrons, free electrons that's inside. And then all the electrons, main reason is because it's attracted by the positive terminal. So these electrons will actually jump and fill up the holes inside there. When it jumps and fill up the hole, obviously this will be a hole already, right, at the side. When it's a hole, the electrons from the negative terminal will keep jumping in the N-type. So electrons will keep on moving towards the P-type semiconductor, and the holes will actually move towards the N-type semiconductor. But most importantly, there is a jump at this part. Electrons and holes can actually move through this junction. When it's able to move to the junction, the electrons can come over to the positive, allowing current to flow from positive to negative. Okay, so when it can, when there is electron passing through the junction, the PN junction, then it's a forward bias. Simple as that only. Okay, I repeat again. When the electrons from the negative terminal move to the N-type, it will repel the electrons, and the electrons at the same timing will be attracted by the hole and the positive terminal of the battery. So when it actually moves between the barrier, the boundary of the N-type and the P-type of semiconductor, the electrons, when it actually move, the PN junction allows current to pass through, then it's actually a forward bias. Okay, so forward bias can understand, forward bias, okay? Processing. All right, you better start processing. My eyes are closing down already. Okay, so for reverse bias, apa berlaku? Something happened to my PowerPoint. Okay, it's not only my head shutting down. Okay, for the record, I'm getting tired and falling asleep, not because of you guys, it's because of after a whole day of teaching Form 6, I drove back from Selangor down with a heavy traffic, so it's a bit tiring for me. All right, so let's go to reverse bias, positive terminal and negative terminal of the power supply. Right now, remember just now my hint, reverse bias is whereby the positive terminal is connected to the N-type. All right. Forward bias is supposed to be positive to positive, negative to negative. So reverse bias, the positive terminal of the power supply, is connected to the N-type of the semiconductor, while the negative power supply is connected to the P-type semiconductor. Now we know that the P-types are actually holes, and the N-types are actually electrons. Okay, and remember from my explanation of the forward bias, the electrons need to pass through the PN junction, the boundary between here. But what happens is when you connect the circuit, all these electrons in the N type of semiconductor, it's attracted to the positive terminal. All right, it's already attracted to the positive terminal. So the electrons from the N type semiconductor will move. All the free electrons at the N type of semiconductor will all move towards the positive terminal. And then all the negative, the electrons from the positive, from the negative electrons, when it reaches here, these are all holes. The holes actually has a tendency to move towards the negative terminal, all right, because it's attracted by the electrons here. So what happens is that the holes are moving towards the negative type, and they actually have a boundary over here. And this particular boundary is whereby there is insufficient holes and insufficient of free electrons. Why? Because the free electrons or n-type is attracted to the positive terminal. The holes are actually attracted towards the negative terminal. There are no electrons jumping at the boundary. Hence, when there is no electron moving through the boundary, this particular yellow area is known as the depletion layer. The depletion layer is whereby the resistance is high and it actually causes the current to reduce. It actually reduces the electricity conductivity. Okay, so hence that's how a reverse bias happens. All right, so that's reverse bias and forward bias. Okay, so reverse bias, if you put a light bulb, the light bulb will not light on. All right, so reverse bias and forward bias, you guys okay? Thank you, Brian. Whoops. Okay. All right. Okay. Okay. Enough with all this. All right. So do you guys want me to explain rectifiers or do you want me to jump to transistor? Rectifier ke transistor? Wait, you give me a minute. Hold on. Mm, let me send a message out first. Let me read. Rectifier. All right, okay, let's talk about rectifier. It's a very quick process. Okay, I'm going to talk about rectifier. Main purpose of a rectifier is actually because Chirong, we're not going into MCO. Okay, let's see rectifier. Okay, let me find for that diode. Okay, I think instead of finding for this, I better draw out myself. One other reason is to keep myself awake. Okay, now, um, rectifiers. Why do we actually build a rectifier? It's because the power supply, right? You know the power supply that you guys have that is nearby you guys right now, whereby there's the 3-pin plug. All right, this actually power supply is an alternating current power supply. Alternating current power supply is whereby the electricity actually oscillates between positive and negative. Right, this is the positive, this is the negative. Now, you try to imagine if your laptop or your handphones is connected to an alternating power supply. What does that actually mean? It actually means that at startup, it will become very bright, and then it starts to get dim. And then when it goes to the negative side, right, it suddenly gets turned off. And then suddenly it gets brighter to the brightest, and then suddenly it starts to get dim again. And then it goes to the negative, which we can't actually have the negative part anyway. So alternating power supply is whereby the brightness keep on changing. All right, from dim to brightest, and then start to dim back, and then towards the brightest, and then coming to dim back. So that is alternating power supply. But our electrical appliances don't use alternating current. All right, so the main reason your laptop, desktop, or your appliances always have the brightest light, okay, main reason is because alternating current they have converted alternating current to direct current. All right, and to convert alternating current to direct current, you need a diode, a semiconductor diode. Okay, so there are two types of rectification. All right, there's two types of rectification. The first rectification is known as a half wave rectification. What does half wave rectification means? Let's just say input. All right, the input is alternating current of positive and negative. All right, so I have this is my input of alternating current power supply. Okay, and then what happens here is that this is the output. Output can be our electrical appliances. It can be a cathode ray oscilloscope. It depends. All right. So usually I would consider it as a cathode ray oscilloscope, easier for us to learn for the time being. Now, if the alternating current is directly connected to the output like this, if the input is alternating current, then the output will be alternating current also. Okay, if it's there's nothing there to convert it. So this is something that we do not want because we don't want an alternating current power supply. All right, we don't want the output to be alternating current. So what we do is we actually put a diode here, a forward bias diode, okay, connected to the output like this. So what happens here is that when this part is positive, current will flow from the positive towards the negative. So when the current, the top part A is flowing positive, the direction is the same, right? So it's a forward bias. So current will flow towards the output and then back to the negative terminal of the input. So the current will actually appear. All right, this top part will appear at the output. But when the terminal switch, all right, because it's alternating current. So when the terminal switch, the bottom part is positive, current will flow here. All right, assuming that it passed through the output. But then when it reaches the diode, the current direction arrow is opposite to the arrow of the diode. So this is a reverse bias. When it's a reverse bias, the current cannot enter back towards the negative terminal of the input. So when this happens, there is nothing appearing down here. All right, nothing is here. Okay, and then when it switch back to the top part positive, then it will appear again because of forward bias. So when the bottom part is positive, nothing happens to the output. And then when the top is positive again, then there's output again. All right, so this is a known as a half wave rectification. So sorry. Sorry. Yeah. All right, so this is actually a half wave rectification. Now, it's only half part of it. So if back to our electricity situation, all right, what will happen is that the our laptop will be on, and then suddenly for one cycle is on, and then for another cycle nothing happened. All right, because the other side is actually positive. So then when the top terminal is positive again, then your laptop starts to switch on again. So it's like your laptop going on and then off. So that's actually half wave rectification. Okay, so obviously That's not what we want. So if that is not what we want, then we will have to turn it into a full wave rectification. Okay, full wave rectification is whereby initially the input is alternating like this. This is AC. Full wave rectification is whereby the bottom part you flip it up. Alright, the bottom negative part we flip it up. So it will become fully direct current. Okay, so in order to draw this, you have to take note. I will teach you guys how to draw 2 times. Okay, so first thing first, input. Observe how I draw this because they will ask you to draw. Input, bring it up, hang it there. Line, make sure that they're in line. Alright, you better learn together to draw together at the same timing right now. Okay? Then I'm making it a little bit longer. Too long already. Okay, and then this is vertical, horizontal, same line, but watch horizontal, I'm gonna jump a little bit, go towards output. And then this one comes to output. Okay, so if you notice over here, the vertical line, they are in line straight, and then the horizontal one is also straight. So what I'm going to do is I'm going to draw the diodes right now. So please do take note. The key to drawing a full wave rectification diode is that the diode must all point to the same direction, either all towards the left or all towards the right. So I'm going to draw, it doesn't matter left or right, as long as it points to the same direction. So I'm drawing mine all pointing towards the right. Okay? So you can see this one is pointing towards the right. This is also pointing towards the right. Okay? Do you need me to draw that again? Hopefully you guys can draw. My brain is shutting down already. All right. Okay. So I am gonna draw again because when it comes to full wave rectification, I'm a little bit the perfectionist on my drawing. So usually what I do is I draw the parallel side first, and it's actually pointing to the same direction. But because this is pointing towards the right hand side already, so the other one also needs to point towards the right. Okay, so that is how a full wave graph looks like. All right, so this one is the input, and here's the output. Okay, so I'm gonna use simulation to explain. Okay, okay. So what happens here is now when this voltage is actually alternating right now. So when it is here positive, the current will move through this diode towards the load, and then it will actually come back here. Uh, All right. Okay. I think using this also very hard for you guys to see. I think I don't understand, then I think you guys don't understand even more than me. I'm gonna label this as A, B, C, D terminals. Input, this is 1, this is 2, here's 3 and 4. Okay? When 1 is positive, current will move from the 1 towards A. Alright, current will move from 1 towards A. And then there's diode. Okay, because that's diode, I cannot use D here. I will label this as E, junction E. And then I label this as diode number 1, diode number 2, diode number 3, diode number 4. So when number 1 is positive, the current will flow from number 1 to junction A. And then what happens? 1 to junction A, cannot go to junction 4. Alright, cannot pass through D4 because this is a reverse bias. So it has to go through D1. Cannot go to D2 because reverse bias again. So they will have to go towards junction B, come to 4, pass by number 3. Whether there is a image output or not, it has to make sure that this yellow color line that I'm drawing comes back to number 2. Okay, so number 3, follow the line, cross over, reach E. Okay, now the main key is actually to come back number 2. So it can go to D4, but no point. All right, so it goes to D3, reach C, and then come to 2. When the current can come back to 2, it actually means that initially the positive part now appears at the output. All right, so the flow of the current when number 1 is positive is 1 to A, to D1, to junction B, to number 4, go to number 3, and then go to junction E, going to diode number 3, then junction C, and back to 2. When it goes back to 2, this positive wave actually appears. Okay? And I'm going to go next already. Now, when number 2 is positive, all right, when number 2 is positive, okay, I'm going to use another color pen. Give me one quick minute. All right, when number 2 is positive, let's try it. 2 is positive, current reach C. All right, remember the main thing is actually to reach the 1 negative. Reach C, current pass through D2, reaches B, cannot go D1 because it's a reverse bias. Pass through 4, come out from 3. All right, and then back to E. No point to go D3 because they want to go to number 1. So it actually passed through D4. When it reached A, can go to D1, but again, no point. Because the main purpose is actually to go back to terminal 1. So when it reaches terminal 1, the bottom part of the wave actually gets to be created at the output. But if you notice one thing, the yellow color arrow and the green color arrow, when it passed from 4 to 3, same direction. So when it's same direction, which means that initially this is at the negative part, now it gets to flip back on top. All right. So when it gets to flip on top, that is where we have our direct current actually. Because the output right now is on top already, the positive part. So that's direct current. So if I'm going to write the path, it's going to be 2C D2, then B 4 3 E D4 A, and then back to terminal 1, which is negative. All right, so this is the full wave rectification. But you notice one thing, the power supply right now, instead of on, off, and then the cycle stop for a while, and then on again, and then off again. But right now what happens is that the power supply here, if I were to use simulation, all right, the power supply here right now becomes what? It becomes on and off, on and off, on and off, on and off, on and off. So we don't want that to happen to our electrical appliances. So if we don't want that to happen to our electrical appliances, we need to do something to the circuit. So what is that something towards the circuit? That is actually our capacitor. All right. So I'm going to copy this slide and paste it again. Let me try to take all this out. All right. So when this is positive, the output will be positive. And then when the input is negative, the output for a full wave rectification is positive again. So again, positive input, positive output, negative input, it gets flipped up to become positive output. But right now, what happens is that it is going on and off, on and off, on and off like that. So what they do is actually they take a capacitor and they put it parallel to the output. When they put it parallel to the output, what happens is that when the power supply actually enters flows, all right, they will charge the capacitor. Here it should be here. All right, it will actually charge the capacitor up, but capacitor has positive and negative terminal. Capacitor is something similar to our power bank. When you charge it, it gets charged to the max, and then when you plug the power bank to your phone or your device, it actually helps to charge the device. So capacitor is a similar function of our power bank. So when the circuit is changing terminals, what happens is that the capacitor will discharge the current out. So instead of being on and off, the power supply right now, initially it gets charged, capacitor charge also. But when it starts to fall, all right, when it starts to fall, the capacitor discharges the current. So when it comes up, then it charges again. So again, when the power supply starts to become lower, the capacitor discharge the current that's inside the capacitor itself. All right. So the output becomes somehow, okay. This is input. Input is alternating. Sorry, I'm starting to get KO already. Full wave rectification is like this. All right. This is without capacitor. All right. But if with the capacitor, when it's supposed to come down, what happens is that when it's supposed to come down, the capacitor discharges and let the current pass through the load. So when it starts to charge, it will charge up again. And then when it switches terminal, it discharges again. So with a capacitor, this is actually what we call a smoothing process. It smoothed out the line. All right. So the direct current power supply, instead of on and off, on and off, on and off, so it will become on all the time. So that's how we have our electrical, our TVs, our devices, right? It's always on all the time, even though our power supply is actually an alternating current power supply. All right. And hence, that is the full wave rectification. Okay. Clear? Yes. It's better to use a full wave together with a capacitor. If your mind is blown, I wonder if you guys actually went through the YouTube link that I sent last time. All right. For transistor, the key for the transistor is actually the base current. I don't think so. I can continue already. I'm so sorry about that because I'm seriously falling asleep already. Let me mana I punya mouse.